I now call to order the Society's 2,454th meeting in the 150th year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's lecture by Nicole Halpern. I'm delighted that today's meeting is being held in person at the Cosmos Club, including a pre-lecture reception and dinner with our speaker. We plan to meet in person regularly going forward and to use Zoom and other social media when it is advantageous in the future. All in-person meetings will adhere to the Cosmos-related rules of the District of Columbia and the Cosmos Club. Proof of vaccination, including a picture ID, will be required for in-person attendance. Masking is required, and we also suggest getting tested for COVID infection within 48 hours of the event. These requirements are subject to change, with changes in the COVID-related rules of the District of Columbia and the Cosmos Club. So please check the PSW website often for up-to-date information. We will be streaming all meetings to YouTube for our remote audience to enjoy and to ask questions in the YouTube chat box. And final versions of the recordings will be posted to the PSW website and the PSW YouTube and Vimeo channels, where they will be permanently available without charge for everyone to view. The Society is grateful to the sponsors of the 2021-2022 lecture series for their support. Please join me in thanking the Policy Studies Organization in cooperation with the American Public University and a generous donor who has asked to remain anonymous. We thank them very much for their generous support. I am pleased to announce the following new members. David Venel, founder and president of Black Rock Automotive, also a pilot and flight instructor, interested in a wide range of subjects, including mathematics, computer sciences, AI, and astronomy, especially exoplanets, who learned of PSW through the PSW Science channel on YouTube. Sybil Russell, a physician with MITRE, interested in a wide range of subjects, especially computer science and behavioral sciences, who learned of PSW from her colleague, Victoria Gamino. And tonight's speaker, Nicole Halpern, who learned of PSW science through PSW member Charles Clark and from the invitation to speak, and whose interest will be clear to you in some small part from tonight's proceedings. We welcome them all to membership. And if you're not a member or would like to join PSW or support the Society, you can do so through the PSW website using the blue Join button on the upper right-hand corner of the homepage. We welcome new members, and we appreciate donations. Recording Secretary James Heelan will now read the minutes of the 2,453rd meeting and the lecture by Roberto Tomai on the European Southern Observatory's extremely large telescope project now being built in Chile. Thank you.
Good evening, everyone. Good to see you all here. On February 11th, 2022, by Zoom webinar broadcast on the PSW Science YouTube channel, President Larry Milstein called the 2,453rd meeting of the Society to order at 8:02 p.m. Eastern Standard Time. He welcomed new members, and the recording secretary read the minutes of the previous meeting. President Milstein then introduced the speaker for the evening, Roberto Tomai, Program Manager for the European Southern Observatory's Extremely Large Telescope, or ELT, project. His lecture was titled, The ESO's ELT, Challenges and Progress on the World's Largest Telescope. Founded in 1962, the European Southern Observatory, or ESO, has a mission to build and operate world-class, ground-based astronomical facilities. The ESO has 16 European member states, with strategic partner Australia and partner Chile. ESO currently operates the La Silla Paranal telescopes in Chile, is in partnership to operate ALMA, is preparing the Cherenkov Telescope Array South, or CTAS, and is currently constructing the ELT. Tamai summarized the instruments and research at La Silla Paranal, ALMA, and CTAS. He then introduced the ELT, which will be the largest ground-based visible and infrared telescope in the world. ELT construction began in 2014 and is expected to take its first images in 2027 as part of La Silla Paranal Observatory. When complete, the ELT will have a 39.3 meter primary mirror with adaptive optics and take images 15 times sharper than those from the Hubble Space Telescope. Tamai showed and explained pictures of the ELT construction site and location at the Cerro Armazones in Chile's Atacama Desert. ELT will benefit from being more than 3 kilometers above sea level with dry weather and clear, stable atmospheric conditions. Challenges will include high UV radiation and high seismic activity. When complete, the ELT will search for exoplanets and explore Earth twins, test the validity of general relativity around a supermassive black hole, resolve star populations, address questions regarding the large redshift universe, and questions of cosmology and fundamental physics. In so doing with such a powerful telescope, Tamai said the ELT's research will lead into the unknown. The speaker then described the ELT's hardware. With a footprint approximately the size of the White House, the main structure will sit atop alt-azimuth mounts to track large objects. Optomechanical units will be jointly capable of realigning themselves, refocusing, stabilizing the image, and computing for external perturbations. The focal plane and embedded metrology systems will measure the state of the telescope and the atmosphere. All of these instruments are necessary to compensate for environmental factors such as gravity, wind, atmospheric turbulence, and earthquakes to stabilize the telescope's images. Tamai then described the ELT's 5-mirror anastigmat concept. Light will first encounter the ELT's main primary mirror, comprised of 798 near hexagonal segments organized in 6 petals, all realigned in real time. Light will then reflect 60 meters to the secondary mirror, 60 meters to the tertiary mirror, then a shorter distance to a 2.4 meter deformable 4th mirror. The deformable mirror will incorporate adaptive optics to compensate for perturbations, before finally reflecting the light to a 5th, fast-tilting mirror that will guide it to science instruments. ELT's first set of instruments will be an adaptive optic imaging camera called Mikado, an integral field spectrograph called Harmony, an infrared imager and spectrograph called Metis, and an adaptive optics system called Maori. ESO is still finalizing the physical composition of these instruments within the ELT. Most contracts have completed their design phase, including the 4 instruments, and are currently in the manufacturing phase. Around a quarter of the contracts have been integrated. Tamai then reviewed some of the ELT's largest contracted works. He described the manufacturing, shipping, and installation processes for the dome and telescope main structure and commented that, although the COVID-19 pandemic halted construction for 1 year, progress quickly resumed in May 2021. The primary mirror and its 133 spare segments will require more than 10,000 components. German manufacturer Schott is manufacturing the 50mm thick mirror segments from a glass ceramic called Zerodur. They are being delivered in batches to another company for finishing. The segment supports have been designed and are now being produced by a Dutch firm. So far, 360 of the 949 segment blanks and 293 of the 936 segment supports have been delivered. The primary mirror also requires approximately 2,500 position actuators plus control electronics and edge sensors. Manufacturers have so far delivered the first batch of each component. Tamai then summarized the production of the ELT's other 4 mirrors, identifying technological specifications and completion timelines of each. ELT assembly and mirror maintenance infrastructure is also underway, and the laser guide star system is nearing its final design. The speaker concluded the lecture by briefly describing the technical specifications and research to be conducted by the ELT's 4 initial instruments, and recapping the site's construction status. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. He adjourned the meeting at 10:01 p.m. The temperature in Washington, D.C., 15 degrees Celsius. The weather, mostly clear. And the number of viewers concurrently viewing on the Zoom and YouTube live streams, 84. And views in the last 2 weeks on the PSW Science YouTube and Vimeo channels, 295. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. Are there any comments on the minutes? For those of you who are on YouTube, you can write your comments in the chat box or email them to corresponding@pswscience.org. Hearing no comments on the minutes, I will entertain a motion for the minutes to be adopted as read. Do I have a second? All in favor? Anyone opposed? Hearing no opposition, the minutes are accepted unanimously as read and will be posted to the website in due course. Again, thank you, James. And we now turn to tonight's speaker, Nicole Halpern, and her lecture on quantum steampunk, Victorian thermodynamics meets quantum computing. Nicole is a fellow of the Joint Institute for Quantum Information and Computer Science, a theoretical physicist at the National Institutes of Science and Technology, and an adjunct professor at the University of Maryland. Her primary research focus is reformulating classical thermodynamics using quantum physics. She likes to call the research quantum steampunk, after the steampunk genre of art and literature in which futuristic technologies are implemented in decidedly Victorian settings. Nicole is an author on many technical papers and presents often on her work. She is also the author of a soon-to-be-published book, Quantum Steampunk, which New Scientist called one of the best science fiction books coming your way in 2022. She also writes regularly on the Quantum Frontiers blog, and her articles and poetry have been published in Scientific American and the Mathematical Intelligencer, among others. Among honors and awards, Nicole's doctoral dissertation won the International Ilya Prigogine Prize, and she was awarded the International Quantum Technology Emerging Researcher Award as a postdoctoral fellow at Harvard. Nicole earned a BS at Dartmouth College, an MS at the Perimeter Institute for Theoretical Physics, and a PhD in physics at Caltech. All questions will be fielded after the lecture during a Q&A session. Nicole, stage is yours.
Thank you for the introduction, and thanks very much for the invitation. It's wonderful to be able to join you here. So I'd like to begin with a technical term, steampunk. So steampunk is a genre of literature, arts, and film. Set in the late 19th century, it encompasses all of the romanticism of the Victorian era, then cranks up the technological level to 11. The steampunk works feature old settings from the 1800s, the Wild Wild West, or Victorian England with some of the first factories and grimy cities and men in top hats, together with futuristic technologies such as time machines, airships, and robots. This blend of the old and the new creates a wonderful sense of adventure and exploration and nostalgia. So people dress up in these steampunk costumes and go to steampunk conventions. I like to say, they dream it. Quantum information thermodynamicists live it. Let me break down that term. The thermodynamics is the study of energy, the different forms that energy can be in, and the possible transformations amongst those forms. It's a very important field in physics, chemistry, and engineering, and biology. It was developed during the steampunk era, the 1800s, because there were these wonderful new technologies, such as the steam engine, and people wanted to understand how it performed useful work, how it made use of energy. I should add that giving a lecture about quantum physics at a philosophical society founded during the 1870s is incredibly steampunk. So I basically could not ask for a better forum. So thank you again. Because indeed, thermodynamics was being founded between the 1820s and the end of the 19th century. So exactly when the society came into being. Again, thermodynamics was motivated by technologies such as the steam engine. People wanted to understand how efficiently it could pump water out of mines or power factories. But it ended up having an influence on fundamental physics because it led people to questions like, why does time flow in only one direction? And what is matter made of? Is it really made of particles too small for us to see? And does it make sense for us to start thinking about those two particles that we can't even see in a scientific context? Thermodynamics was developed for the cutting edge technology of the day, the steam engine, which is large and classical. By classical, I mean described well by physics developed before the 1920s. But the cutting edge technology of the day has changed between then and now quite a bit. We have great control over small systems. So this is a single strand of DNA. You can take one end of it and trap it and use a laser, optical tweezers, to stretch the strand. Then you can measure the work required to stretch the strand through a given distance. What's of great interest, especially to me, is quantum physics, which very loosely speaking is the physics of the small, a few atoms, molecules, particles of light, etc. This over here is a picture of one of the refrigerators that Google uses to cool down one of its instances of its quantum computer. It's a dilution refrigerator. Its quantum computers consist of superconducting qubits. Superconductivity is a phenomenon in which current can flow forever without dissipating. And it's a quantum phenomenon. It's exhibited by quantum materials only when they're at very low temperatures, which is why they need these large refrigerators in order to cool the systems. But cooling, the expulsion of heat, the expulsion of the energy of motion, is a thermodynamic process. Many of us are interested in information processing and how information processing plays together with thermodynamics. I will argue that there's a very close connection. And since this is a quantum computer, which I'll describe a little bit more later, it is an information processing device. A system that's in equilibrium is rather boring if you look at it at a large scale. Its large-scale properties like temperature and pressure just remain constant. And there's no net flow of anything like particles or energy into or out of the system. So it looks pretty boring. And a lot of the thermodynamics developed during the 1800s was built for systems in equilibrium. But so much of the world is out of equilibrium. You and I are out of equilibrium. That's how we can be living beings. And there are also a lot of quantum experiments about out of equilibrium systems, especially now. People will take a bunch of atoms and basically hit the atoms, whack them so that they come out of equilibrium, and then people will watch how they get back down to equilibrium. All of these settings are very different from the old conventional thermodynamic setting that we saw before, but thermodynamic concepts such as heat and work remain relevant. So we need a new toolkit for re-envisioning the thermodynamics of the 1800s for the science that we're doing today. Quantum information theory provides such a toolkit. By quantum information theory, I mean the study of how we can use quantum behaviors in order to process information in ways impossible if we just have classical systems like the cameras and computers that are being used to put on this talk. By information processing, I mean solving computational problems, communicating information, securing information cryptographically, and storing information in memories. There are many different quantum phenomena. Some examples include entanglement, which I'll talk about more later. You can think of it as very strong correlations between that quantum particles can share. There's the phenomenon of non-commutation. We're used to numbers that commute with each other. 2 times 3 is the same thing as 3 times 2. So the order doesn't matter. But quantum physics features numbers that don't commute. You can't exchange their orders. And that lies behind some very deep quantum physics. So if you measure a quantum system, then you'll disturb it. For instance, if you try to measure its energy, then you can actually change its energy. And that can be a fundamental disturbance that you can't get rid of. Also, quantum systems have only certain values of energy that they can have. We just gained energy over dinner because we were eating food. And so you could have eaten your entire dessert or half your dessert or a quarter or any little fraction that you wanted. So you could get any amount of energy at all. A quantum system could eat only certain discrete amounts of its dessert, loosely speaking. So it can have only certain possible energies. And there are other phenomena that we could talk about. The quantum information theory, like thermodynamics, has in part been motivated by the promise of quantum technologies, such as quantum computers, which can outperform the computers that we have today, even supercomputers, in solving certain computational problems. There's a whole different paradigm for computing. There are some experts on quantum computing in the field. I'm not going to focus so much on the technology of quantum computing, but on the mathematical and conceptual toolkit to which it gave rise. Now we think about the quantum world in terms of how it stores and processes information, as though the quantum world naturally is something of a computer if we just know how to look at it in the right way in terms of how it's manipulating quantum information. So quantum information theory is a mathematical and conceptual toolkit being applied to many different subfields of science to gain new lenses onto them. So condensed matter, black hole physics, computer science, chemistry, atomic, molecular, and optical physics, and thermodynamics. So you can take the thermodynamics of the 1800s and update it for the 21st century using this toolkit of quantum information theory. You get this field of quantum thermodynamics, or what I call quantum steampunk. It involves a number of goals. We take the old laws and concepts of thermodynamics from the 1800s and update them so that they can apply, they can govern small quantum, far from equilibrium and information processing systems. We know that some quantum phenomena can enhance information processing, as by speeding up certain computations. So there are information processing tasks like computation. Similarly, there are thermodynamic tasks like powering a factory and charging a battery and so on. If quantum phenomena can help with information processing tasks, then can they also help with thermodynamic tasks? Also, we can look at the set of thermodynamic behaviors that are possible and ask which of these are really possible only in the quantum realm, which of them are really non-classical, really incapable of being realized in the everyday world. So this collection of questions and aims, since it blends the old and the new, I call quantum steampunk, very much based in both Victorian history and cutting-edge technology and science. But here's where I'd like to go in the rest of this talk. But first, I'll try to convince you that it does make some sense to put together quantum information theory with thermodynamics, to use that as your toolkit for updating the science of energy. Then I'll try to convince you that work, which comes from thermodynamics, since it's energy, useful energy, and information from information theory, both can serve as resources in both settings, in computation and in thermodynamic tasks. Then I'll dive into one subfield of quantum thermodynamics that is under active research today, that of quantum thermal machines. We are very familiar with thermal machines. These powered the cars or metro trains that got us here today. What if they were quantum? What would they look like? How would they differ? So I'll talk about one of those, and then I'll talk about the opportunities for this field. But why does it make any sense to try to use quantum information theory to update thermodynamics? So about this slide, when I was making this talk, I basically, to amuse myself, peppered the talk with steampunk artwork. So if steampunk is not your aesthetic, then I apologize, but it kept me entertained, so hopefully it'll at least keep you awake. The big question in information science is how efficiently can we process information? And the answer I like to call the liver of information theory. But when I was in 9th grade, I had a biology teacher who said, if you ever don't know the answer to a question on a test of mine, write down liver. The liver performs a ridiculous number of functions in the human body. So if you don't know the answer to a biology question and you try liver, you have an anomalously high probability of being correct. Similarly, if someone asks you, what is the best efficiency with which we can perform some information processing task, and you answer a function of an entropy, you have an anomalously high probability of being correct. An entropy is a function of a probability distribution or the quantum state of some particles. It is a measure of how uncertain we are about the value of a variable distributed according to this probability distribution, or what outcome we will obtain if we measure a quantum system in this state. To proceed farther, I need to give a little bit of background about quantum information theory, and in particular, the qubit. The qubit is the basic unit of quantum information. It's the quantum analog of the bits, which is the classical unit of information. So a bit we can think of as something that can be in one of two possible states, such as left or right, or 0 or 1, the answer to a yes or no question. A qubit is realized in a physical quantum system as a quantum system that, for example, might have two of those possible energy values that I discussed before. Or another example for those familiar with it is the spin of an electron. So quantum systems have a property called spin that's very similar to angular momentum. Everybody has angular momentum if they are spinning like a ballerina or a figure skater. And a quantum system has a property that is described by exactly the same math as angular momentum. It's just something that ballerinas and figure skaters don't have because they're not quantum. But you can think of it the same way. A qubit is in a quantum state. So if we have some classical system, some collection of particles, then we'll describe its state by specifying all of the particles' positions and momenta, where are they headed, with what speeds. The state of a quantum system is as close as we can get to an analog of the state of such a classical system. Technically, a quantum state is a trace-one positive semi-definite linear operator, which sounds like a lot of jargon, but it makes a lot of sense when you think about it in terms of what it means. So, let's see. Here we go. An operator is just some mathematical objects. A linear operator is some particularly simple mathematical objects. Positive semi-definite basically means if you measure a system that is in any quantum states, then there are different possible outcomes of the measurements, and there are different probabilities of obtaining those possible outcomes. Then the trace one means if you measure the system, you will definitely get some outcome. We represent a quantum state with this symbol rho. I know that the general public has been learning a lot of Greek letters thanks to the various variants of COVID. I think we haven't quite gotten to rho, but maybe someday the quantum state will be glorified in COVID terms. Hopefully not. Yes, then maybe quantum physicist funding will dry up because people will be unenthusiastic about rho. We represent the state of a qubit with a point on this sphere called the Bloch sphere or inside of it. There are two types of quantum states. There are pure states. These are represented by the points on the sphere. You can also represent such a state with this other Greek letter, psi, also either hopefully it'll become a variant of COVID or hopefully it won't, depending on your point of view, how much you love quantum physics. Again, this is represented by an arrow, a point on the sphere, or an arrow that extends from the center of the sphere all the way out to that point. An arrow pointing upward represents the quantum analog of the 0 bit that we saw earlier. This downward pointing arrow represents the quantum analog of the 1 bit that we saw earlier. And since a quantum bit is not restricted to 0 or 1 like a classical bit, a quantum bit's state can be represented by an arrow pointing in any of the directions. And we call these other directions superpositions of 0 and 1. Another class of states consists of mixed states. This is the state of a quantum system that's entangled with another quantum system, so it shares very strong correlations with the other system. Again, we'll see more about entanglement later. The state of a mixed state is represented by a point that's inside of this Bloch sphere. And the shorter the arrow is, the closer that point is to the center, the more entangled our qubit is with some other quantum system. A favorite example of thermodynamicists is what we call the thermal state. Suppose that you have a little qubit and it's interacting with a big environment that has some temperature, heat. Then it will end up in this thermal state that's an exponential. The H here represents basically the energy of the qubit. This K is Boltzmann's constant, just some constant of nature. You can ask the people from NIST who are here a whole lot more about constants of nature if you wish afterward. And that Z over there makes sure that this quantum state has all of the properties up on the left-hand side. So if you measure the state, you'll get some outcome with some probability. But now that we have this background about qubits, let's see one of these entropies face to face. Let's see that the entropy does quantify the maximal efficiency with which we can perform some information processing task. For example, suppose that I have a message that I would like to send to Larry. We agree in advance on the quantum letters that I might be sending him. And Larry also knows the probability that I'll send A, the probability that I'll send B, and so on. He is not sure which letter I'll send, so in his view, I'm sending some quantum states in which all of the possible letters are weighted by their probabilities. Suppose, for mathematical convenience, that I actually send him many, many copies of this message. Suppose that I want to squeeze the whole message into as few qubits, basic units of quantum information, as possible. I'm performing the information processing task of data compression. How many qubits do I need per copy of my message? The answer is given to us by Schumacher's theorem, which says that in the limit as the number of copies gets very, very large, the number of qubits I need per copy of my message approaches this quantity, the von Neumann entropy, which is, think of as some function of our quantum state. And if you want a full explanation for why the function has that form, then you can check out the book. Or ask during the question and answer session. Okay, so an entropy does serve as the optimal efficiency with which we can perform some information processing task, but why is this thing called an entropy? The answer comes to us from Claude Shannon, who founded information theory in the first half of the 20th century. This is a Google Doodle from his 100th birthday a few years ago. Shannon said that he talked to his friend von Neumann, whose entropy we just saw. John von Neumann was one of the great Hungarian-American mathematical physicists of the 20th century. And Shannon said that von Neumann told him you should call it entropy for two reasons. In the first place, your uncertainty function has been used in statistical mechanics, which is more or less thermodynamics, under that name, so it already has a name. In the second place, and more important, no one knows what entropy really is, so in a debate, you will always have the advantage. That's why I do information theory and thermodynamics. Indeed, here is the fundamental relation, very important equation in statistical mechanics, which is, again, very closely related to thermodynamics. There's a lot of back and forth between the two. So here's the equation. So imagine that we have some physical system, the steam in a steam engine. It's undergoing some process, so its energy is changing. So the dE on the left represents the change in its energy. And the right-hand side of the equation shows us how that change in energy can be attributed to multiple different causes. So the first term has the system's temperature and the change of its entropy. The second term has its chemical potential, which is related to how much the density of particles in the system. And this dN means, well, maybe the number of particles in the system is changing. If you get some particles, for instance, again, if you ate your dessert, then you got some energy. And indeed, here is the entropy in statistical mechanics, more or less thermodynamics. In statistical mechanics, also, the entropy represents an uncertainty. We said earlier that if you have a classical system, like the steam in a steam engine, and you want to describe its state, then you should specify all of the positions and momenta and so on of these particles. But it's really, really hard to measure the positions and momenta of all the particles in a cloud of steam. We basically can't do it. Instead, we can just attribute to the steam some probability of being in this state and some probability of being in that state, and so on and so forth for all the possible states. So there's this probability distribution over all the possible states. And how spread out that probability distribution is number one, a measure of how uncertain we are about the state of our system. And number two, it's the entropy. So in thermodynamics, as in information theory, entropies represent uncertainty. Okay, so thermodynamics and information theory have conceptual overlaps. They both deal with entropy and so on. But can they really help each other? I will argue that the answer is yes. I'll start with Szilard's engine. Leo Szilard was another great Hungarian-American physicist of the 20th century. And he argued that if we have information, we can use it to turn heat into work. So heat is random energy. We're radiating heat now. It's not being used for anything in particular. It's uncoordinated. So it's kind of useless. And we often denote heat by a Q. On the other hand, work, another type of energy that is transferred between systems, is useful. It's coordinated. You can directly use it to charge a battery or push a rock up a hill, and so on and so forth. So it's useful. Often denoted by W. So if you have information, you can turn this less useful heat into more useful work. Let's see how. Suppose that we have a classical particle in a box. This will be a very, very simple ideal gas. Suppose that the gas exchanges heat with a fixed temperature environment through the walls of the box. I'm calling the environment a bath. In the tradition of statistical mechanics, you could call it an environment if you like, but I like using the word bath because then I can think of loofahs and soap and so on in the cartoon world of my mind when doing thermodynamics. Suppose that we start with one bit of information about this gas. We know that it's in the right-hand side of the box rather than the left-hand side. We can slide a partition into the box and tie a rope to the partition and tie an Acme anvil to the rope, and then unfix the partition so that it can slide. The particle is going to hit the partition, and it's going to keep punching the partition until the partition gets to the opposite side of the box. Now, we have lifted the weights. We have done work on the weights against gravity. The weight has gained gravitational potential energy. Where did the energy come from? It came from the heat bath, from the environment. And how much work can we do on this particle? It's a very simple calculation. It's the work of pushing against something. So it depends on pressure, P, and it depends on how far the gas pushes. So the change in the volume, which I've represented by dV. Now, in high school, we learned the ideal gas law. The pressure times the volume of the gas equals the number of particles times Boltzmann's constant times the temperature. We can solve that equation for the pressure and substitute it into our integral. So I'm integrating from V over 2 to V because the particle begins confined to half the box, V over 2, but ends up able to be anywhere in the full box, V. So we integrate, we evaluate limits, and we find that the amount of work we can perform on the anvil is Boltzmann's constant times the temperature times the natural log of 2. So that's how much work we can perform. But at the end of the process, even though we've performed work, we've gained work, we have lost our information because we now have no idea where in the box the particle is. So we traded our information for work. We can reverse this process and perform what's called Landauer erasure. Suppose that we begin with a particle that can be anywhere in the box, and we want to reset it to one side so that we know where it is. This is like taking some messy sheet of scrap paper and erasing it to a nice, clean, pristine state. We can slide a partition into one side of the box, hook up our anvil, and then use the anvil to push the partition into the middle of the box so that the particle is definitely trapped on the right-hand side. Since we're compressing a gas, we have to perform work. And again, that amount of work is at least Boltzmann's constant times the temperature times log 2. So we performed work, we gave that up, but we gained information. Now we know where the particle is. This story has deep implications for the relationship between computation and thermodynamics. Suppose that we want to compute and compute and compute and compute. Eventually, we're going to run out of scrap paper. We're going to have to erase scrap paper. And we just saw that erasure costs thermodynamic work. So computation has a fundamental energy cost. So computation is fundamentally linked to thermodynamics. When I first learned this, my final year of college, it blew my mind. Because computation and thermodynamics seem like very different fields. Why should they be related? But they do have this very fundamental relationship. Okay, I've been telling you about a classical particle in a box, but gosh darn it, this talk is called quantum steampunk, so how can we bring quantumness in? In order to do that, I need to provide a little bit more background. This is about the entanglement that I kept referring to. Entanglement is a strong relationship that quantum particles can share and classical particles cannot. It manifests in the correlations between the outcomes of measurements of the particles. And again, these correlations can be stronger than any you can create with just a classical system of particles. A very simple state is called a singlet. In a singlet state, loosely speaking, we have a qubit A that's in the 0 state that we saw before, while qubit B is in the 1 state, and loosely speaking, and at the same time, qubit A is in the 1 state, while qubit B is in the 0 state. So for example, suppose that Gandalf and I have a pair of particles, A and B. We bring the particles together and perform some operation on them so that they're entangled, and then we bring the particles to opposite sides of this room. Then if either of us measures our particle locally, then we have no idea which outcome we'll obtain. For instance, Recall that sphere that represents the possible states of the particle. Gandalf could measure, is my particle pointing upward or downward? And he would have no idea which possible outcome he'd obtain. But each of us could measure, and there are some sets of measurements that we could perform such that we could predict something about the outcome. So suppose that each of us measures, is the particle pointing upward or downward? Then if Gandalf receives the down outcome, he knows I'll receive the up outcome, and if he receives the up outcome, he knows I'll receive the down outcome. Furthermore, there is a measurement we can perform on the two particles jointly such that we can predict the outcome exactly with complete certainty. So there's something that's not in my particle, it's not in his particle, and it's not in the sum of the two separate particles. Instead, it's in the whole, or it's sort of between the particles. It's in the relationship between the particles. But when it comes to entanglement, the whole is greater than the sum of its parts. Let's use that entanglement in our thermodynamic erasure of information. Suppose that the system that we want to erase or reset is not the location of a particle in a box, but instead a qubit. And we want to reset the qubit so that it's pointing upward. Suppose that our qubit is entangled with some other system, which I'll call a memory. And again, there is a heat bath around that we can use to perform or extract work. Then we can erase this qubit while extracting net positive work, while gaining work for ourselves. That should be surprising because we just saw that erasure costs work. We have to pay in order to erase. And here I'm saying we're gaining work. The trick is that we can sort of burn the correlations between the system and the memory so that the entanglement in the presence of a heat bath sort of serves as a thermodynamic fuel. So in summary, we can use information to turn useless heat into useful work, and work as well as information, including quantum entanglement, can serve as resources in both thermodynamics and computation. I thought it might be fun at this point to dive a little bit into one of the subfields of quantum thermodynamics that's under active development now. That's of quantum thermal machines. The example that I'll give is of one quantum many-body engine. When I say many-body, think many particles. So not as many particles as are in you and me and the air in this room, Avogadro's number, but more like tens or hundreds of particles. This engine is based on the phenomenon of many-body localization, which is a horrible term. It has so many syllables. Sometimes I'll use the acronym MBL. I try to avoid acronyms in talks, but I really will need this one for a reason that I'll show later. So many-body localization is a phase of quantum matter. We're used to seeing different phases of matter, such as liquid, gas, and solid, but quantum systems can be in totally different sorts of phases. So here's how this one can look. Suppose that our quantum many-particle system is a bunch of qubits in a line. You can realize this with, say, very cold atoms. Then our system's energy can be governed by the following principles. So I'll show the math that will be meaningful to some people. It won't be meaningful to other people. But the nice thing is every single piece of math has a physical interpretation. So we can all end up understanding it all. According to this part of the energy, two qubits that are next to each other will repel each other. They don't like to be up at the same time. And also, if there's one qubit up next to a qubit that's down, then they can flip simultaneously. And this process happens with a frequency 1 over what I'll call J. The other term we call disorder. We can think of it as characterizing the background landscape on which our qubits live. This landscape is very random, very jagged. So if you try to prepare a sample, maybe in the lab, where these qubits will live, and you see that your background looks like this, then you'll probably think, oh, this is a dirty sample, I should throw it away. And in fact, my collaborator, Gil Raphael, likes to call it random crap. But random crap can actually be really useful in the context of many particle quantum physics. And if we have, say, ultra-cold atoms that are serving as our qubits, then this very jagged background can be created by an optical lattice, which is formed by propagating laser beams. We can think of this background as follows. Suppose that we want to know how high the jag, or high or low the jag is on some particular qubit, j. Then we'll pick a random number between -1 and 1. I'll call that h sub j. And multiply that number by the overall strength of the disorder, the overall sort of typical height and depth of the peaks and valleys. I'll call that h. So that's how strongly disordered the system is. So if the disorder is really strong compared to the frequency with which these up qubits hop around, or the state of being up hops around, and you measure where the ups are, then the qubits will stay in this configuration for a long time, as though they're approximately frozen. That behavior is in sharp contrast with the behavior that we're more familiar with, of equilibration. Suppose that you have a much more familiar system, a system of just a bunch of particles. Suppose you measure all of their positions. And suppose you find that they're all clumped together in one corner of their container. Very soon afterward, they will spread all across the container. So they're not going to stay approximately frozen for a long time. So in this sense, many-body localization behaves not like an ordinary thermodynamic system that will tend to spread out. And a system that tends to spread out, as we are used to seeing systems do as time flows, a system that resists that behavior is called athermal. So many-body localization behaves in an athermal way. And systems that are athermal and not, say, at the same temperatures as their environments and not spreading out can serve as resources in thermodynamics, in thermodynamic tasks like the extraction of work. We can see this through a simple example. Suppose that we're in an environment at a high temperature T sub h, and we're suddenly given a much colder system, so that there's a difference between the two temperatures. We can let heat flow from one system to the other, and from that heat flow, we can extract work via an engine. Work is useful. For instance, we use it to power our cars. So it makes sense to think of this colder system that's not, just like it's an environment, and it hasn't allowed the flow of time to make it just like its environment. This other system that's athermal, that's not like its environment, is a resource. So if systems that are away from thermal equilibrium are resources, then can we take advantage of the way that many-body localization is not at thermal equilibrium? So, of course, the answer is yes, otherwise I would not be giving this talk this way. And with some collaborators, I illustrated that the answer is yes in a paper. So we designed, this is why I had to introduce the acronym MBL. We designed a quantum many-body engine that we dubbed the MBL Mobile. It is an engine that can be in this many-body localized phase of matter. And we designed an Otto cycle for it. The Otto cycle is a set of 4 steps that we use to power cars. So again, there are 4 steps in the cycle. During 2 of them, the engine's entropy remains constant, and during 2, the volume remains constant. So usually if we illustrate how an engine operates, then we'll maybe draw along one axis of a plot the volume and along another pressure. But those characteristics aren't the most relevant to our quantum thermodynamic system. So I will illustrate with quite different axes. Along the x-axis, I'll have the ratio of the disorder strength to the frequency with which the excitations, the state of pointing upward, hop around. So if the disorder is low, it's not very strong, then the system is very shallowly localized, so the particles really can hop a decent amount. Or in an actual extreme, then the system is in a totally different phase of matter, where particles spread out quickly, and this is, we would say, a thermal phase of matter. If the disorder strength is large, then the system is very deeply localized. Along the y-axis, I will plot energies of our many particle system. I said earlier that a quantum system can have only a few particular energies. It can't have any energy in the real number line. And we're often interested not in just one physical system, but in a whole class of physical systems. Like I showed earlier, Hamiltonian, the energy function of these particles. And we saw some h sub j's there. Those were random numbers. And so you could pick many different random numbers and get many different instances of that energy function. And they would form a whole class. And classes of systems of classes of many-body quantum systems have different statistics of the gaps between the possible energies. So suppose that you have one of these classes of quantum many-body systems, like a class of many-body localized systems. You randomly pick a system from this class, and you look at its Hamiltonian, its energy function, and you find what its energies are. And there are gaps between the possible energies. And what is the probability that any given gap is of size delta? That is the essential quantity, that probability, that characterizes energy gap statistics. It turns out that different classes of quantum many-body systems in different phases, can have really different energy gap statistics. So if the system is just shallowly localized or even in its thermal regime, then the energy gaps typical energy gaps tend to approximately equal the average gap. And if the system instead is deeply localized, then small gaps and large gaps come up much more frequently. So we start off our engine cycle with the engine in it very shallowly localized and at thermal equilibrium with this hot bath. So the engine state is in one of these thermal states that we saw earlier. We can imagine that the engine is on starts on one particular energy with some probability. So this energy level was chosen according to one of these probabilities. So at the beginning of the cycle, we start here. We disconnect the engine from the hot environment, and then we change the strength of the disorder from low to high. We approximate that change as very, very slow for some technical reasons, although we can calculate corrections. And we see that this energy of our engine is moving downward in energy space. It's moving downward along the y-axis. According to the first law of thermodynamics, energy change in the system is either heat or work. We've already disconnected our system from the heat bath, so what's coming out is not heat, so it's got to be work, which is useful for us because we want for our engine to perform work for us, to put out work. So that's work. And our engine ends on this energy level in the deeply localized regime. During our second step, we hook up the engine to a much colder bath, and we demand that the bandwidth of this cold bath, which is the greatest energy minus the least energy, is not too big. Since this difference is called the bandwidth, I represent that quantity with a W sub B. And this bandwidth should be much smaller than the average gap, which we assume stays constant across the cycle. And so the engine, it will try to cool down because of the cold bath, but the cold bath can accept packets of energy only if they're small enough. only if they're no greater than WB. So this cold bath will cool the engine across just these small gaps that appear more commonly in the deeply localized regime. So the engine spits out a little bit of heat and moves down here. Then we lower the disorder strength so that the system, the particle or the qubits can spread out. And again, the energy moves downward in energy space. The engine moves downward in energy space. And again, the energy that comes out of the engine is not heat, so it must be work. So the engine ends here. And then during the final step, we hook the engine back up to the hot bath so it can replenish itself. So it'll take in some heat. On average, the engine performs a positive amount of work, which is useful because it needs to perform work for us. Why does it perform positive work? Because we trace out this trapezoid that has its narrow snout in the deeply localized regime. So whenever the engine's disorder is changing, the engine moves downward in energy space, outputting positive work. That's why the engine works. And we can put the narrow snout of that trapezoid in the deeply localized regime because the deeply localized regime has more small energy gaps because of its energy gap statistics, which are very different from the energy gap statistics of the thermal phase of matter. So this engine, it does seem to work according to the previous picture, but it actually has a problem. Suppose that we call the number of qubits in our engine n. Then the bandwidth of our engine, the greatest energy minus the least energy, will be proportional to n. But the number of energy levels grows like 2 to the n exponentially. And the number of energy gaps, differences between consecutive energies, also scales exponentially. And so the average gap will decrease exponentially as the system grows. And we saw that the average gap is, according to our picture, is greater than the average energy, the average work performed by our engine. So as the engine gets very large, the work performed approaches 0. That's not very useful at all. So we can solve this problem by appealing to that other athermal property of many-body localization, namely localization. Stuff doesn't spread out a whole lot in our engine. So we can create a sub-engine of about 10 qubits. The power, average work outputted will be exponentially small just in this number, which doesn't grow as the whole system size grows. And then we can chain sub-engines next to each other so that, and we don't need to worry that influence from one engine will interfere with a neighboring engine because of localization. So the whole engine will have some n total qubits, and the power will grow with this number, with the total number of qubits, because it grows with the number of sub-engines that are all performing work. And again, this works because what happens in a sub-engine stays in a sub-engine because many-body localization is naturally localized. Stuff doesn't spread out as in a thermalizing gas. We evaluate an engine by calculating its power and efficiency. The average work per cycle we found is proportional to the total size of the whole engine, and also the bandwidth of the cold bath. So the greatest energy minus the least energy of the cold bath. And there are some corrections because our cold bath isn't at 0 temperature. That would be very useful, but realistic baths aren't. And when we change the disorder, it's not, we don't change it at an infinitely slow speed. So that's just some mathematical results, but what does that look like? We did some very rough estimates by imagining an engine formed from phosphorus doped with silicon. So this platform had not been used at the time to realize many-body localization, but a different type of localization that's close enough for our purposes. The power seemed to be about 10 to the negative 16th watts. What does that mean? According to our rough calculations, it's about 10 times the power of another small engine, the one that powers the flagellum of a bacterium. We can also estimate the power density, or power per unit volume. That seemed to be about 100 kilowatts per meter cubed. What does that mean? It's about 1/10 of the power density of the engine in a car. So we will probably not see MBL mobiles in our garages anytime soon, but the MBL mobile performs not too badly. You can check this with numerical simulations of a many-body localized system. My collaborator, Christopher, simulated a chain of 12 qubits. We'd like to test this prediction that the average work is about the bandwidth of the cold bath if we have just one sub-engine. So along the x-axis, we have the cold bath's bandwidth in units of the average gap. Along the y-axis, we have the average work in units of the average gap. The red dots are the numerical results, and the blue line represents the theoretical prediction. And the agreement is quite good. Surprisingly good, since the only parameter regime in which we expect the theory to be good is this little gray bar. But the theory seems to predict well, even quite outside that regime. We also evaluate an engine through its efficiency, which is the average work that it performs divided by the heat that it takes in during the step in which, on average, it takes in positive heat, so the final step. That turns out to be 1 minus the cold bath's bandwidth over twice the average gap. And we've already assumed that the bandwidth of the cold bath is much smaller than the average gap. So this subtracted off correction is small, and the efficiency can be good. Moreover, this efficiency of the MBL auto engine can equal the efficiency of a conventional thermodynamic ideal gas auto engine. Suppose that I'm a conventional thermodynamic agent and I have an ideal gas auto engine. Then I will compress and expand it between these two volumes, V plus and V minus. And this gas has heat capacities at constant pressure, C sub P, and constant volume, C sub V. So those determine the efficiency. What do I mean by this equal sign? Well, I will have this gas with these heat capacities. I will choose volumes between which to expand and compress. I can achieve this optimal efficiency. And then suppose that Bruce is a quantum thermodynamic agent. He has an MBL auto engine. I can hand him my numbers. He can choose a cold bath bandwidth and an average gap such that his engine achieves the same efficiency. Both of these efficiencies, fortunately, are no greater than the Carnot efficiency. This is the greatest efficiency you can achieve with any engine that runs between just 2 different heat baths with 2 different temperatures. And this makes us happy because if we break the Carnot bound, then we are probably violating the second law of thermodynamics, and so we are probably doing something very, very wrong. The MBL Mobile has a few advantages over particular competitors. I can provide details about those later. We saw that it can grow robustly because of its natural localization. Relatedly, it can have a relatively high power density. It's also relatively reliable. If you run an engine cycle many, many times, then you'll get different amounts of work out. We'd like for our engines to be reliable, so we want the fluctuations from trial to trial to be small. And they are relatively small in the MBL Mobile because of its energy gap statistics that are very different from the energy gap statistics of a thermal quantum system. And relatedly, the number of worst case trials is relatively low. If you run an engine enough times, eventually the amount of work that it outputs is going to be negative. So it's going to cost work to run. I call these worst case trials. And the number of those is relatively small, again, because of energy gap statistics. But what is ahead for quantum thermodynamics and quantum steampunk? Well, as far as the MBL Mobile goes, experimental realizations are possible. Many-body localization has been realized with a number of platforms. And I'm actually working with people on trying to realize this with superconducting qubits. Second is optimization. So this engine, we argue, works, but it is not the best possible engine you could build from a many-body localized system. So you could play tricks to try to improve it. This work also initiated the application of many-body localization to thermodynamic tasks. People had already guessed, maybe we could use many-body localization to store information in a quantum memory because the particles aren't going to move around and destroy the information we encode. We showed that just as this quantum phenomenon might be useful in information processing, it can be useful in a thermodynamic task. There are many different thermodynamic tasks, so we might be able to design other materials from many-body localization for them. For instance, you could dream of having a many-body localized refrigerator that services quantum many-body systems. You tend to have to get quantum many-body systems at low temperatures for them to exhibit quantum phenomena. So you might have a quantum refrigerator that services other quantum systems. And so localization and energy gap statistics that are very different from those in the thermal phase can, in general, serve as resources in thermodynamics that we just hadn't thought of as resources before. More broadly for quantum steampunk, I think is one of the most important opportunities is to interface with other fields. So quantum thermodynamics is a broad landscape with many different subfields, not only quantum thermal machines, but much more. But quantum thermodynamics itself is embedded in a much bigger landscape where there are many different communities of people who are interested in quantum physics, information, and energy. So we can try to use the tools of quantum information and thermodynamics to answer questions in other fields or gain inspiration to ask new questions about thermodynamics. Other fields have developed particular tools for addressing how a system thermalizes, and so we can try to integrate these toolkits. Also, quantum thermodynamics traditionally has been very theoretic, but fortunately experiments have gained momentum in the past few years, and they are going to continue gaining momentum. Also, one intriguing opportunity that I think exists is to take on the spirit of the Industrial Revolution. During the Industrial Revolution, technological advances went hand in hand with the development of theoretical thermodynamics. In quantum thermodynamics, we've discovered really interesting, I think, fundamental theory and understood our world in new ways. It would be nice also to have that theory feedback on technology and be really useful, practically. In summary, we saw that quantum information theory serves as a mathematical and conceptual toolkit for reimagining the thermodynamics of the 1800s. We saw that both information and work can serve as resources in both thermodynamics and computation. We saw one example of a quantum thermal machine, the MBL Mobile. We saw that it's in a phase of matter, many-body localization, that can be seen as athermal, away from thermal equilibrium with a constant temperature of the environment and particles moving around randomly. We constructed an engine cycle for a material that can be in this phase. We calculated the power and the efficiency. We saw that there is much to be done. But in case you are hooked on this topic, I can recommend first a couple of reviews on quantum thermodynamics. These came out originally in 2015, and this field is moving really quickly, so a lot has happened since then. But these are great for starting to understand the foundations, especially the quantum information theoretic take on thermodynamics. Also, as was mentioned before this talk, I'm publishing a book about quantum thermodynamics this spring. It's called Quantum Steampunk, The Physics of Yesterday is Tomorrow. It was written for the general public, including scientists. So I hope that people from many different backgrounds get many different things out of it, and I'll just have fun learning with it. Also, does anybody recognize this painting? Does anybody here belong to the National Academy of Sciences? Or has anyone been inside the headquarters? Okay. Does that hint help? I don't know. I've only been to one. with the giant Einstein sculpture? Okay. I've been there only once. But when I was in college, I interned in DC at the Smithsonian Libraries. I had just decided on my major. So I had just sold my soul to the physics department. And I wanted to learn more about what this scientific life that I had signed up for was like. So I, as a college student, wandered into the National Academy of Sciences headquarters. I wandered past security. I don't know why they let me in. And I found myself facing this beauty in or right near the lobby. This painting is called Everything at Once or One Thing at a Time. It's by the artist Robert Van Vranken. It is wonderfully steampunk. It has these old features, like it might be a little hard to see on the slide here, but there's some beautiful columns and some hand pencil drawings, but there's this aspiration as shown through the view of the sky and the globe and some mathematical designs. So it definitely caught my attention. And it plays an important role in this book and in quantum steampunk, because what is a superposition of up and down? And what is a quantum measurement that jars a system out of being in a superposition and forces it to be one or the other? What are a superposition and a quantum measurement if not answers to the question, everything at once or one thing at a time? So this painting is in the book. It's not there pictorially, but it's embedded there in a few different ways. So if you find it there, then I hope you enjoy the reference. And if you end up again in the National Academy of Sciences old headquarters and you find this painting, then please give it my fond regards. So again, if you take the quantum information theory of the 21st century and use it to reimagine the thermodynamics of the 1800s, you get this fusion of old and new that is quantum steampunk. So steampunk fans dream it, quantum information thermodynamicists live it. Thank you.
So thank you very much, and we have time for the Q&A, and I have to do my little spiel here about the question and answer period. So the procedure is, if you want to ask a question, raise your hand like Frederica is doing right now. Be persistent. Eventually, one of the runners who have microphones will come to you and give you the microphone. It'll be on. You don't have to do anything. Please don't mess with the settings. But I ask you, do hold it close to your mouth so we can hear you. And so the people who are watching online can hear you. And so the people who watch the video recording afterwards, which is the majority of people who are going to watch this lecture, can hear you. I'll call on people by the color of their microphone. So Frederica has a blue microphone, but we're not ready yet. Hold on. Be patient. And I will call on blue microphone. That way I don't have to memorize everybody's name. And then that person will stand up, say their name, tell us if you're a member. There's no penalty for not being a member. And then ask a question. For YouTube viewers, you can type your questions in the chat box, and Cameo at the back of the room will ask those questions aloud so the speaker can hear it, and so those who view it are viewing on YouTube and also later view the recording will know what the question is. So with that, let's take our first question from the blue microphone.
Thank you. My name is Frederica Derima. I'm a PSW member. It's basically inside my mouth. Thank you very much for the very nice presentation and giving us quite a bit of the background of quantum information systems and your approach of integrated thermodynamics and quantum information system. And you talked about, in a sense, processes. So I'd like to, the processes that you described were more of the adiabatic form. I was at IBM TJ Watson when Charlie Bennett started talking about quantum computing, and he and I were physicists, so we talked. And I asked him, Charlie, that's very nice, but it seems to me that I can see how it applies in adiabatic systems, but how do you do turbulent fluid dynamics? And Charlie thought for half a minute or so and said, Frederica, good question. A few years later, actually, I asked also Rolf Landauer, whom you mentioned in your presentation, same question. Frederica, good question. We're talking about mid-80s or towards the later part of the mid-80s. It's about almost 40 years. Still remains maybe a good question, but I was thinking whether with your formalism, maybe you can make progress in that. So what do you think about how your formalism can, in a sense, help us represent? Because it's a matter of how we represent, all right? If you have an adiabatic process, a diffusion equation, Hamiltonian or a diffusion equation, yes. But if you have turbulent fluid dynamics, you need Navier-Stokes, for example. So how do you think your approach can help in that? Or if you, okay, I can ask a follow-up afterwards, right? I can ask also a follow-up afterwards?
If it's quick.
Yes, it will be a quick after your answer.
Did you get the
Yes.
question?
Okay, I can give an example of how this framework treats non-equilibrium processes. So, so there are two meanings of adiabatic. One is more in thermodynamics, and it means that heat cannot enter or leave the system. And the other is used more in quantum physics. And in this case, adiabatic means basically very, 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 very slow. So do you mind if I just pick one, or do you have one in mind?
You can choose whichever you like,
Okay.
or both.
Okay, so I'll go with quantum adiabatic. And also, very, very slow processes are common in thermodynamics, and I agree that just focusing on very, very slow processes is very much a limitation, because a lot of what happens does not take an infinitely long time. So I mentioned that quantum thermodynamics has many different subfields, and one of them that's really originated within statistical mechanics is fluctuation relations. So I showed an image of a strand of DNA and said that we can use optical tweezers to stretch the strand and measure the work required to stretch the strand through a given distance. That's one experiment that has been used to test fluctuation relations. So people here have probably heard of the second law of thermodynamics. I know you, of course, would be very familiar with it. And the second law of thermodynamics basically tells us something about why time flows in just one direction. For every closed isolated system, the entropy just grows or stays the same. It cannot decline. So it's an inequality. The entropy of the system at a later time is greater than or equal to the entropy at an earlier time. This is an equality which is not exact. It doesn't tell us how much the entropy grows or what the entropy is going to be. So it leaves a lot of room for potential improvements. And I think of fluctuation relations as in some way strengthening the second law. They're equalities. The second law of thermodynamics is an equality only when the system is at equilibrium at every step in the process, and so the process takes a really, really long time. But fluctuation relations hold even when the system is far out of equilibrium, as it'll tend to come to be if we perform a process quickly, like if we pull a DNA strand quickly. And so those fluctuation relations started in classical statistical mechanics and have made their way into quantum thermodynamics and quantum information. That's one way that I think of in which the more modern version of thermodynamics focuses on and even can take advantage of non-adiabatic or quick processes.
Can I ask my follow-up, please? Sorry. So I think it's good that you can address fluctuation, but also I want to push back a little bit because it's a matter of scale, of how fast these fluctuations. And if you have, let's say, in turbulent fluid dynamics, aerodynamics, that I asked the question, I think it's a different kind of scales. So, but anyway, I hope you have a good tools and you can address it one day. I think I would appreciate and answer the question that nor Rolf Landauer or Charlie Bennett had been able to answer and has not been answered for all these years. And also, I want to thank you for pointing this photo at the National Academies, because I have been there many, many times, as so have my colleagues, and I had never noticed it. So next time I go, I will look for it. Thank you so much again for your presentation. Great work. I mean, we need to, in a sense, push for making progress towards this direction. I think it has a lot of promise, but also we don't want to overpromise and underdeliver, as we know has happened in some other field.
Yes.
So congratulations again for your work. And
thank you.
I hope
I agree that different settings require different toolkits. And yeah, so I just described one, but there could be others that more are suited to the setting that you have in mind.
We have a question from the web from Bill Phillips, who is actually a member of the National Academy, so maybe he knows the picture.
Hi, Bill. Thanks for listening in.
We have a question from the chat, as Larry just mentioned, from Bill Phillips, member and Nobel Prize winner. Question is, thermodynamics is about large systems. Much of quantum mechanics is about small systems, yet it seems that thermodynamics still applies, even to small systems like two entangled particles. Could you comment?
Sure. And this was, let's see, quantum thermodynamics has a history that stretches over many decades. The most recent wave of quantum thermodynamics has, I think, succeeded in convincing a number of people across the physics and chemistry communities that it's worth countenancing. But an objection that squelched some quantum thermodynamics some decades ago was that thermodynamics describes large systems, quantum theory describes small systems, and so never the twain shall meet. But I think of thermodynamics as an operational theory and so it's about agents who are performing tasks, and they want to perform the tasks as efficiently as possible. They want to charge batteries, they want to run engines, they want to run generators, they want to pump water out of mines. So we can imagine performing these tasks with large systems or with small systems. In both cases, we have operations that we need to perform, and we have energy moving into and out of the system. So I think that those properties are more fundamental to thermodynamics than the largeness of the system is. And so that's why I think that it can make sense to take ideas that are key to thermodynamics, like heat and work, and extend them to the quantum scale.
Any follow-up question there? Cameo?
There does not seem to be a follow-up question, but another question from the chat from proud due-paying member Will Angel asks, what areas of quantum mechanics research are you most excited about?
Well, the research that I'm doing now, I think, is a very common answer. So at the moment, I'm working on a part of quantum thermodynamics that involves another one of the phenomena of quantum physics that I mentioned near the beginning of the talk, non-commutation. We're used to 2 times 3 equaling 3 times 2, the number multiplication commutes. But in quantum theory, there are observables of the system, like energy and the number of particles, that don't have to commute with each other. And we can have a little system and a big environment exchanging things, like energy and particles. This is a very, very common setting throughout thermodynamics. It too describes the dessert that we ate tonight. And in basically all of thermodynamics, we assume that the things exchanged by the little system and the big environment are represented by numbers that commute with each other. This assumption was implicit in some arguments, and just no one really realized it until a few years ago. But if we have quantum systems, then they can have observable, measurable properties that don't commute with each other. And these properties can be quantities that you can exchange between a system and a bath. And so my group is studying what happens when you take this really common problem across thermodynamics and make it even more quantum by adding in the non-commutation of these quantities exchanged. So we started off using the tools of very abstract quantum information theory and now we've bridged those to experiments. So we just put out a paper with a group in Innsbruck in which they had a chain of qubits formed from trapped ions. So they realized one of our predictions. Now I'm working with some condensed matter theorists. They're trying to approach this problem from many different perspectives and see what truly non-classical observations we might make about this thermodynamic system.
Could you say just a couple of words about what properties are not commutative?
Sure. So suppose that we have a qubit. Then we said that we could measure whether it points upward or downward because it has this property of spin that's like angular momentum. And but our qubit is in a state that's represented by some point on the sphere, so it can be pointing in any direction. So this qubit has spin angular momentum that has a component in the z direction and the x direction and the y direction. And these three different components of momentum are represented by operators that don't commute with each other. So you can imagine a chain of qubits formed from trapped ions. And each of the qubits might have some quanta, some packets of spin angular momentum in the x direction or the y direction and the z direction. And these quanta of spin angular momentum are moving around between the different particles.
Okay. Let's go to the blue microphone.
Hi, thank you very much.
Name, member?
Bob Terry, I'm a member. Fascinating talk. 3 questions.
Three
Why?
questions. Do they commute?
They don't commute. Why 2? Why is a qubit only a 2-state system? Could you not be working with 3-state, 5-state, 20-state systems? And if you have a physical candidate for a qubit in your laboratory, how do you decide if you want it to be a 2-state, 3-state, or 20-state system? And third question, where is time?
I'll start with the first 2 questions. So a qubit is a 2-level system by definition. You're very welcome to make 3-level systems and use those for information processing or other experiments. Those are called qubits. And a system with d levels, for d between 2 and as large a number as you please, those systems are called qubits. So it's certainly possible and sometimes fruitful to think about quantum systems with more than 2 levels. It's useful to think about qubits because the qubit is the smallest possible unit of quantum information. Just as the bit is the smallest unit of classical information, it's the information that an event that has one of 2 possible outcomes, like yes or no, has this outcome rather than that outcome. You're excluding one outcome, and so you have the smallest possible amount of information. And we like to break things into basic units like seconds and pennies and so on. And other NIST people here, if I'm talking about not really fundamental units, then don't call me out on that. But we like using fundamental units. So that's one reason why we use qubits. There are people who work really hard to realize qubits in labs. And that can be useful in some ways. For instance, if you have a quantum computer with qubits, and so you could sort of line up a competition. Suppose that you want to solve some computational problem. You can try solving it with a classical computer. You can try solving it with a quantum computer with qubits. You can try solving it with a quantum computer with qubits. And loosely speaking, the classical computer would need a really, really long time. The quantum computer, well, if it's in a certain class of problems on which quantum computers have an advantage, the quantum computer of qubits would need a shorter time, and the quantum computer with qubits would need an even shorter time. But qubits can be really difficult to control because they can, even more easily than qubits, couple to their environments, so stray magnetic fields, any little particles around. And as soon as they've interacted with something else, they're sort of dirty. They've leaked out quantum information from the computer.
Is 2 a bit fortuitous, or can you generally get the same kinds of theorems that you're showing with 3-element objects or 5-element objects? Is there something special about 2? Or not?
Often you'll have a theorem that will be phrased in terms of qubits, and you might be able to rephrase it in terms of 3-level systems. Just some of the precise numbers in the equations will change, but the overall forms of the equations will change the same, or will stay the same. We just like thinking about basic units, so that's why we often think about basic units of quantum information qubits.
Okay. Talk about time. Time.
Oh, yeah, where's time?
Good question.
There are a number of ways in which we could think about time in the context of thermodynamics. One is connected to the second law of thermodynamics, as I discussed before. So according to there are multiple ways to phrase the second law of thermodynamics. One is that in every closed isolated system, the entropy of every closed isolated system grows or remains constant. And if the system is in thermal equilibrium, so its large-scale properties are not changing, then you can't tell that time is flowing because everything's more or less the same all the time. But it's the descent to thermal equilibrium during which we can tell that there is time because the entropy of the system is changing. And so if you want to measure time, you need a clock that is not at thermal equilibrium.
Bob,
I'm asking, does this model admit transport theory? Does it admit change over time, like any number of classical and quantum statistical mechanical theories?
I'm afraid I don't quite understand the question.
Okay, I have something that's heated, and I put a flame to it, and I predict what the temperature is in all space and time as my flame goes up and down, moves around space, washing over it. Is there an equivalent transport theory you can build with these units, which enables me to study the same problem?
So I'm afraid I don't understand the question.
perhaps you could talk about this
Yes,
afterwards. Yeah. I think, though, that the question of time on the quantum scale and the Planck length is an open question. And
Yeah,
if you remember Carlo Rovelli's talk and his books, he suggests that maybe time is a kind of, the concept is a mistaken concept of operating on the macro scale. But, you know, it's a longer discussion. I'm sure Carl would love to pursue it. But we're going to go to Bruce's question. The red microphone there.
Yes, I'm Bruce Kane. I'm a member, and my question is, what aspect of your engine requires a mini-body system? Can you envision a single non-interacting particle in a disordered potential and extracting work from that as well? Or do you explicitly require many-body interactions?
Right, so there are 2 ways to think about this question. One is, suppose that you had just one particle and you were trying to run an engine from that. Then you could do that just fine. And in fact, there are quantum auto engines that consist of single qubits. But we were interested in an engine that could scale up. And so it could be somewhat, you could imagine it as somewhat comparable to a classical engine, which is also of a decent size. And so we were interested in giving our engine good scaling up properties, which we can't do if we have just one qubit. Another way to look at that question is, suppose that we have a system that's not many-body localized, so the particles don't interact with each other. Instead, we have an Anderson localized system. The particles are still localized, there are multiple of them, but they don't interact. Our engine cycle would work, but it wouldn't be quite so convenient because you would have to tune the interactions on and off during the cycle, which would seem kind of awkward, especially since you have to keep certain ratios of certain properties the same across the cycle. And so it seems easier just to let the interactions be in the system the whole time.
Carl?
member of the society. I just wondered, I'd like to hear your comment. David Deutsch has claimed that if you could have a quantum computer that actually worked, this would be proof of U. Everett III's many world hypothesis. And I just wondered what your thoughts on that are, or whether I know a lot of people don't want to think about that. They just calculate. So I just wondered what you would say.
Yeah, David is a very strong proponent of the many worlds perspective on quantum theory. Some people don't even like to call it an interpretation. They say that the many body worlds perspective is just taking quantum theory seriously. And there are a lot of those people at Oxford. I think that this study of the foundations of quantum theory and the quantum measurement problem are very interesting. I like learning about it, and I have spent some time learning about it, but I think that in order to put forth an opinion about it, I need to be more of an expert on it, and my expertise is in another area. So I like keeping an ear on this conversation. I think it's very interesting, and David is a very sharp thinker, but I should refrain from putting forth an opinion about it.
We have another question from the web.
Yes, we've got a follow-up from Bill Phillips. If a quantum computer is reversible, does the thermodynamic arrow of time matter? Does doing error correction change that?
So a quantum computer is ideally reversible, but as you sort of allude to, the computation is not reversible in practice because we don't have a perfectly clean setup for our computer. So errors will come to be defects in the computation. And in quantum error correction, at least in some popular quantum error correction schemes, we have to measure the computer. So we measure an error syndrome to figure out what errors have disrupted the computation. And after we figure out what the error is, then we perform some error correction to try to put the computer back into more or less where it needs to be in the computation. And whenever we perform a measurement, then we're collapsing a quantum state. So we're performing an irreversible step. So I see that as at least one place where time comes into quantum computation.
Thank you.
Are there more questions back there? Cameo? Nope. All right, then we'll go to the blue microphone. Al?
My name is
Name?
Al. My name is Al Ehrlich. I'm a member of the society. Is that explanation you just gave for the direction of the time arrow related to this fact that I've read but never understood, that if you drop something with order, some kind of order like a human body or something, into a black hole, the energy contained within that human body, the order of it, where things are, is that why I find it incomprehensible to imagine that information still being retained after the thing has gone through a black hole and maybe come out the other side or something?
So this is closely related to the black hole information paradox. Suppose that some individual, Alice, has a diary in which she's written a secret, so some information in some ordered object. She doesn't want for anyone to read her secret, so she throws the diary into a black hole. And someone else, Bob, would like to find out what the secret is. So a black hole will radiate. It'll radiate particles of light. And this is Hawking radiation. Bob can stay outside the black hole and collect the Hawking radiation. And according to at least, we're not entirely sure what happens to the very last bits of the black hole, but they might also come out as Hawking radiation. So suppose that Bob collects all the Hawking radiation. The Hawking radiation, if he just looks at any piece of it, it looks like it's at thermal equilibrium. Basically, its only notable feature is that it has some temperature. And it doesn't look like it has it's very highly entropic. So we can ask, where did Alice's information go? Did the information just disappear from the universe? That is inconsistent with some beliefs that many physicists hold about the universe as a whole. Well, the pieces of Hawking radiation are entangled with each other. And as we saw at the beginning of the talk, if you have an entangled system and you just measure one piece of it, or you just measure this piece and this piece and this piece and sum up the results of your measurements, then you can't get all the information about the whole system. There's something that's in the entire collection of Hawking radiation in the relationships between the particles. So you could, in principle, imagine performing a really complicated measurement on all of the Hawking radiation so that you can reconstruct Alice's secret. That would be really hard.
So the complexity, if it's
No,
still
you just have
there.
Speak up, further away, and now speak up.
Okay. So the complexity, if it's still there, could be reconstructed in principle if you knew where you got each of these pieces out of the black hole and maybe the order in which you got them when they arrived. Would you have enough information then?
And maybe if you had a really powerful quantum computer and you ran the right algorithm, then you could sort of take the information that's spread all across the pieces of Hawking radiation and put it back together in the right order.
You'd have to have an algorithm that told you where your information went or not when it was dropped into the black hole.
Constructing the algorithm would take some thought. People have written some papers about this, like my PhD advisor.
Thank you very much.
We have a question over here. We're going to bring the blue mic over to this questioner. Blue mic. Name, are you a member, and a question?
George, not a member presently. Question on applications, and what would you know of someone who may have been looking at applications of this type of thermodynamic extraction of work? Instead of trying to grow a system larger, trying to grow a system smaller, but still be useful, more in the nano mechanics or a nano machine kind of mechanics. Is someone trying to apply this for a nano machine?
Let's see, I think of quantum thermodynamics as encompassing quantum and small-scale classical systems. So the way that I often think of the nanoscale is that it's basically classical, although I'm open to being corrected, as I don't spend most of my time there. So certainly there are things like nanomechanical oscillators that will exhibit quantum behaviors. And yeah, there was actually an experiment done at Oxford within the past, I think, couple of years, in which there was a membrane that was nanoscale and classical, and it was driven just by random noise. But because of how it was configured, it actually ticked like a clock. And the experimental group measured the relationship between either the precision or the accuracy of the ticking and the amount of entropy that dissipated that they could measure separately. So there are possible applications to nanoscale machines like clocks in this way, possibly engines, though I guess usually nowadays I think more about the quantum scale.
Are there any more questions? Seeing as how there are no questions, let's thank our speaker for sharing her time with us and for giving us talk. And before you go, we have an actual real copy of something you pictured in one of your first slides.
Thank you.
Which is volume 1 of the Bulletin of the Philosophical Society of Washington, where you'll be happy to read why they called it the Philosophical Society and who founded it, who the original members were, what their purposes were, and especially interesting, no doubt, will be the minutes of a meeting in which one of the speakers provided a new method for calculating pi to 38 decimal places. So,
Thank you.
thank you so much. Before we go, there are a few closing announcements. We hope the next meeting will be in person. We're planning for the next meeting to be in person, but we are, of course, ultimately at the mercy of COVID and COVID-related rules. So keep looking at the website and check the dinner invitation lecture announcements. For additional information, our next speaker is going to be Melissa Hawkins, who is at the Smithsonian Institution's National Museum of Natural History. She is going to be talking about exploring biogeography and evolution with ancient and modern DNA. What we mean by ancient DNA here is DNA in museum specimens. Some of you may know the Smithsonian Institution is one of the last remaining repositories of actual biological specimens in the country. It has a tremendous collection of type specimen and other kinds of biological collections. And she's one of the leading researchers who's extracting DNA from these specimens and using it to do taxonomy, or what we call systematics these days, and to look at the distribution of species, to define species, to understand extinction, and to explore some of the relationships in ecological systems. So it should be a really interesting talk. And she specializes in squirrels. For those of you who are squirrel lovers, you'll get to see a lot of squirrels from around the world. And I'm a squirrel lover, so I'm looking forward to the talk. She also works on lemurs. And those of us who like squirrels, generally speaking, like lemurs. After that, lecture 2456 on March 25th will be Kim Prather, who is at the Scripps Institute of Oceanography, University of California, San Diego. And she's an expert on aerosols and ocean spray. And she's going to be talking about aerosols from the ocean spray and the communication of all kinds of things and the aerosols all over the world. And she's also going to be talking a little bit about how aerosols carry viruses, and particularly COVID. And some of you may remember that we had a talk by Rami Amaro. And Rami works with Kimberly and did modeling on virus particles inside aerosols. So this is a kind of follow-up to that in part. I don't have the April 8th speaker, but I will soon. The April 22nd speaker for lecture number 2458 will be Elizabeth Strychowski from the National Institutes of Science and Technology. And her talk will be the minimum genetic complement. So she'll be talking about work done to take the mycoplasma genome and get rid of all of the extraneous genes in it to define the minimum complement of genes required to sustain a cellular life form. The interesting thing is not just the genetic engineering of the genome, it's also that you had to control the environment in order to define what genes are necessary. And she had to make these kind of nano reactors and to do that. So it's a very interesting combination talk. The rest of the schedule is not here. I will tell you we are going to have a talk, I think it's May 20th, by the engineer of the Ingenuity helicopter on Mars. So that should be fun. So check the website often to get updates. And before we go, let's thank our crew here tonight. As you can see, there are quite a few people who helped get this on to video and stream it to the web. So I have Robin Taylor and Bill Goodwin in the back there who are running the show and streaming to the web. We have Brett Magaram and Noah Block and Robert Thompson running our cameras. We have Cameo taking care of the chat. Mark Clampin, who did the check-ins for us but isn't on here. Laurel Kane's on here, but she was not here tonight. So Lloyd Mitchell was running mics for us, and we thank him, and various other people who have also helped. So with that, I will now adjourn the 2454th meeting of the Society. You can hang out for a little bit and continue the discussion. And I wish everyone a good morning, evening, afternoon, or night, wherever you happen to be. Meeting is adjourned.